into trigonometry world. Last time we discussed law of sines. We still have to come to class during the final? Well, you have to appear on Zoom for the final. It's as if you're taking another exam. So if that's what you mean, then yes. Okay. So yeah, Felipe, if you have any questions about the homework, please let me know now. What exact problems are we speaking of? One, two, three, four, five, six, seven. That's it. That's a lot. I don't know if we have time for all of that, but we can definitely get some of them. Just pull it up. So 1, 2, 3. Let's see. Yeah, I'm pretty sure the first few shouldn't be a problem. If after you see one of them, I don't think. Yeah, I'll do this. I'll do. Yeah, some of these it's not a problem at all. So homework number. This is homework number 10, right? So for example, number one, I'll show you. You can do number one very easily. Number one, I have a right triangle like this. I got a right angle, 45 degrees. This is 36, and this is x, right? If you guys remember, this is a 30. Okay, I'll do two ways, right? Solution number one. Solution number one is when you look at the angle that's presented, and then you see the sides that are given. Well, this side here is opposite 45 degrees, and this side here is the hypotenuse because it is opposite the 90-degree angle. So what you can say is this is what? Sine of 45 degrees equals the opposite side, which is 36, over the hypotenuse side, which is x. So we can do that, for example. And we should know that sine of 45 degrees is rad 2 over 2. We should know that already. And then we have a proportion that we can solve by cross multiplying. And we get that x rad 2 is equal to 36 times 2. So x rad 2 equals 72. Divide by rad 2, because I want to get x, right? And I get that x is equal to 72 over rad 2. And then if you want to rationalize, you multiply by rad 2 over rad 2, and I get that x is equal to 72 rad 2 over 2. Then these 2's here cancel into the 72, and I get, finally, my answer, 36 rad 2. So this is like the standard way of getting the solution. That's nice. Or you can do this in like 10 seconds because this is a 45, 45, 90 triangle. If you guys remember, a 45, 45, 90, and let me just put it in this. Let me invert this here. If this is 90 degrees, this is x, this is x, this is x rad 2, and this is 45 degrees, this is 45 degrees. And the moment you tell me this is 36, then the hypotenuse has to be 36 rad 2, so I'm done. Number one is done very quickly if you remember or recall or know the 45, 45, 90 degree triangle. And the same thing goes for the next 3 or 4 problems because all of them are either a 3690 triangle or a 45-45-90. So if you look at number 2, number 3, they're 30-60-90 triangles. I'll do one of them. I won't do all of them. Okay, I'll do number 3. I hope that makes sense. So this is number 3. Number 3, we have a right triangle. This is also 90 here. This is X. This is 60 degrees. And this is 19. So I'm going to do 2 ways again. I'm going to do it the standard way, which is just to say, okay, we have an angle. We have its opposite side and the hypotenuse side, which means that I'm going to use sine of 60 degrees. That equals X over 19. And I already know what sine of 60 is. Sine of 60 is rad 3 over 2 equals X over 19. And then all I need to do is to get X by itself. So multiply by 19 on both sides. And I get that X is equal to 19 rad 3 divided by 2. That's it. You could have also done the other way with knowing the dimensions of a 30-60-90 triangle. So this is 2x, right? And this is 60 degrees, this is 30 degrees, and opposite 30 degrees is X, and opposite 60 degrees is X rad 3. So if you know that this is 19, because that's what they give me, right? They give me 19. I want to find the opposite side of 60. Well, the first thing I know is that I can figure out what X equals. X equals 19 over 2, which is this side right here. And then once I know X, I can just attach the rad 3, and the answer should be 19 rad 3 over 2. So again, these are the type of problems that you're given in the first batch. Any questions about 1 and 3? Do you guys understand what's going on here? And I'll do 2 more. I'll do number 5 and I'll do number 6, and then we can move on. So number 5 is a bit different because the angle is not a nice angle. When I mean by nice, I mean it's not 30, it's not 45, it's not 60, it's 39 degrees. So this is kind of like a bit off, right, from what we are normally accustomed to. So this is like more, this is what happens in real life, I should say. Our angles aren't so pristine and nice like 30, 60, or 45. So we have a 39-degree angle, and then we have an opposite side and an adjacent side. So if it's opposite over adjacent, then we're using tangent for this. So tangent of 39 degrees is equal to the opposite side over the adjacent side, X. And I want to find X, so then I can treat this as if it was a proportion. I cross multiply, and I get that X times tangent of 39 degrees equals 11. I want to get X by itself, so I divide both sides by tangent of 39 degrees. I didn't plug anything in yet into my calculator. I just left it as tangent of 39 degrees because that represents a number. Not necessarily sure what it is yet, but I'll find out later. X equals 11 over tangent of 39 degrees. You put this in your calculator and you should get a decimal answer, right? And I get 13.58387. They say round to the nearest 5 decimal places. So those are my 5 decimals. And that's how you do this one, right? You just find the trig ratio and then use your calculator to find the value. That's number 5. Number 6 and number 7 are similar. So I'll just do number 6, and then you can try your hand at number 7. So number 6, it looks different, right? It looks different than what you've normally been accustomed to. This is theta, They call this y, they call this x, and they call this 16. And then they say express x and y in terms of trigonometric ratios of theta. Basically, they're just saying for x, for this side, find an expression for this side that has theta in it, and find an algebraic expression or trigonometric expression that represents this opposite side in terms of theta. So theta has to be part of the expression. So it's all about the expression of, of the answer. The answer is not a number, it's an expression. So then if I want to figure out what y is, right, I just have to see what is y and how is that related to theta? And then how else can I relate y and theta together? And the only other known side I have is 16. So it makes sense to use sine. Sine of theta equals the opposite side over 16. And now I just want to get y by itself. So y is equal to 16 sine theta, and I'm done. That was it. So y is 16 sine theta. I have found y. I have found what this side is in terms of theta. There you go, sine of theta. And then the same thing goes for x. How is x connected to theta? Well, x is the adjacent side, so cosine of theta equals x over 16, which implies that x is equal to 16 cosine theta. And I'm done. Okay. So that's a quick, blitz through the first 7 problems. Very similar. The first 5 are very similar. 16, 17, they're all very similar. It's just, they change a bit, and the last 2 problems are more algebraic in nature, but the variable is always on top. Well, of course, it isn't always on top. Always, be careful with the word always. It's very strong. It's not always on top. It could be on the bottom. We had variables. Yeah, look at number 5. Our variable is in the denominator, so it doesn't have to be in the numerator. We just have to be mindful as to what kind of ratio we're setting up. So in this problem, it makes sense to make y, right? To use y, theta, and 16. And you notice that this has to use what? Sine. Sine of theta relates the opposite side with the hypotenuse side. That's why the y here appears on the top. And for the x side, right, it makes sense to use 16, theta and x, to find the relationship. So you could have tried this, x and y, but the problem is you have a lot more variables than you need. I don't want a whole bunch of variables. I want things that are known with things that are unknown. So it makes sense to find cosine theta, which is the adjacent side over the hypotenuse. And that's why x appears on the numerator in this one as well. It's not because it's always true. It's just because in the context of this problem, it just so happens to be true. Okay. Anything else? Make sense? Question 25. Question 25. Okay, question 25. I'm glad, Felipe. I'm glad it was helpful. 25. So we have cosine of angle, right? Equals 4 over 11. And then we're also given that sine of theta is less than 0. Okay. Cosine of theta. So for this problem, you have to first figure out where is theta. Which quadrant is theta in? So to do that, right, you have to figure out from this segment here, cosine is positive where? Where is cosine positive? Cosine is positive in quadrant 1 or in quadrant 4, right? That's where cosine is positive. And then it says sine is negative. What does that mean? Sine is negative where? Quadrants 3 or quadrant 4. And the one that coincides in both of these different trig information, right? The only quadrant that coincides for both of them is quadrant 4. So then the deduction, what we conclude is that it must be in quadrant 4. That's what it must be. So theta is in quadrant 4. So once you're in quadrant 4, the only thing that's positive in quadrant 4 is cosine. Everything else will be negative. So sine will be negative, tangent will be negative. Okay, and then I want to figure out what? I want to figure out sine of theta. I want to figure out cosine of theta. I want to figure out tangent of theta. And then once I have these, I can have the reciprocal. It's just the reciprocal cosecant, secant, and cotangent. It's just a reciprocal of the sine, cosine, and tangent. And once I have that, all I need to do now is create a right triangle of any sort, create one of those angles to be theta, and then I want to fill in the information that I'm given from the beginning. Cosine of theta of this angle is 4 over 11, which means that the adjacent side is 4 and the hypotenuse is 11. Now the question becomes, what is the opposite side? Well, that's when you use what? That's when you use the Pythagorean theorem. So you say 4 squared plus 11 squared equals, pardon me, 4 squared plus x squared equals 11 squared. So 16 plus x squared equals 121. So x squared is equal to 121 minus 16, which is 105. So x is equal to square root of 105. So this side here is the square root of 105. And then that's the hardest part. The hardest part was to figure out the other side of this right triangle that you constructed based upon the information that they give you. Once I have all three sides, then I can figure out all sine, tangent, and cotangent, and so forth. Sine is the opposite side, which is rad 105. And the hypotenuse is 11. Boom, I got that. Once I get this, then I know cosecant theta, right? It's just 11 over square root of 105. Cosine, I'm already given that, which makes this a lot easier. Secant theta is 11 over 4. Tangent is what? Rad 105 over 4. So that means that cotangent is 4 over 105. And don't forget, because I'm in the fourth quadrant, sine has to be negative. Cosecant is negative. Cosine is positive, but tangent has to be negative. So don't forget about the negative sign. So that's how you do 25. And of course, your numbers might be different. They might change up the numbers for cosine, but the idea is the same. The idea, find where cosine is. Find where theta is. So you have to compare both of the trig ratios and the information they give you to figure out what quadrant you're in. Once you establish the quadrant, you're able to figure out which of the trig ratios is positive or negative. And then you create this right triangle with the given sides to find the missing side using Pythagorean theorem. And that's how you do this one. Okay. I hope that makes sense. And then number 7 of Felipe is very similar. It's very similar to number 6 that we just did. I would let you guys try to figure that out. And like I said, theta here is what you want at the end of your solution. So if you look at the triangle for number 7, you have 9 on the adjacent side of theta. And look at x. X is opposite, right? And y is hypotenuse. Just look at the x for now. If you look at x, what kind of relationship is x with theta and 9? X is opposite theta and 9 is adjacent to theta. So what makes sense to use is tangent of theta. Tangent of theta equals x over 9. And once I find that out, I want to get x alone. So I know I'm saying things in the air, but I'm only going to do this half one, okay? And then you figure out the other one. So this is number 7. This is theta, this is y, this is x, this is 9. What do you notice? X is opposite theta, and 9 is adjacent to theta, so it makes sense to say tangent of theta is equal to opposite over adjacent. But after this, I want to get x by itself. So what must I do? I must multiply by 9 on both sides. The 9's cancel, and I'm left with x is equal to 9 tan theta. That's it. That's all it is. I'm gonna let you get the other one, the y side. Again, it's the same idea. See what relates to what, and then um, solve for the missing variable. That's all. That's all they're asking for number 7, which is similar to number 6. Okay, guys. Nine over y, but it was wrong. Of course, it's wrong because you want to find y, Chen. You want to find y equals something with theta. So it's cosine theta equals 9 over y, but I want to find y. So guys, this is just the algebra part of it. Okay. Okay, so cosine theta equals 9 over y. This is correct. The answer is wrong because you're not supposed to plug in like this. You want to get y by itself. And once you get y by itself, what is this? This is really just algebra at this point. I want to do this. I want to go from here and I want to say y equals blah, blah, blah. So how do you get y in this equation? How do you get the variable y to just be alone on one side of the equation, everything else on the other side? There's many ways. One way you can is multiply y on both sides. If you multiply y on both sides, the y is no longer in the numerator, and now you get y times cosine theta equals 9. But what's the goal, guys? Get y by itself. So then what do? Divide by cosine theta. Divide by cosine theta, and look what we get. Y is equal to 9 over cosine theta. I did it. Or I can rewrite this as 9 secant theta because it's 1 over cosine. So I said I wasn't going to do it, but I did it. Do you see that? That's all it is. It's algebra. A little bit of algebra at the end. Algebra is always going to be sprinkled in. All right. Okay. Guys, also, part of this whole homework stuff, any homework is, it's part of the nature is to try to figure things out. And I know it's not easy, but that's the whole idea behind it, is to try to figure out something that at first seems a little bit difficult. And then you realize it's not as bad as it is. All right, guys. So let's continue. Let's continue with trig. We got a quite number of things to still cover in trig. If you don't, it might be surprising to hear that, but yes. So last time, right, we talked about law of sines. And then naturally you might ask, but is there a law for cosines? And of course there is. So we're going to talk about the law of cosines. So with the law of sines, you needed a pair of an angle with a side. So if you had two pairs of an angle with side, you can apply law of sines. In this case, what the requirement is, or I should say the prereq for this, the prerequisite are the following. You need 3 sides. You need 3 sides, and you only need one angle. That's it. Now, what could be unknown are various, so there's different scenarios to use the law of cosines. There's 2 different scenarios that you could use the law of cosines. One scenario is if you don't know one of the sides, but you know everything else. Or the other scenario is when you know all 3 sides, but don't know the one angle that you're given. So those are the 2 different scenarios. So let me draw just a random triangle. Doesn't have to be right. So for these problems, Um, for these problems, we don't need a right triangle. We just need a triangle. So I'm gonna call this A. This will be B, and this one will be C. And remember, we name our sides with respect to the opposite angle or vertex. So these are my vertices here, A, B, and C. So the side opposite big A will be called little a, lowercase a. The side opposite uppercase B is known as little b, and the side opposite big uppercase C is little c. So then what is the law of cosines? How do you write that? Well, it's written this way. And it might take a little bit of exercise to see it, but this is the formula. So it's c squared equals a squared plus b squared minus 2ab times cosine of c. That's the law of sines. I mean, pardon me. This is the law of cosines. It's a bit more complicated than the law of sines. So I just want to highlight a few things. C is opposite C. So C is opposite big C. I should say, I'm gonna call this angle C. So side C is opposite angle C. AB are just the AB and this AB are just the sides that are not opposite C. They're the sides that make up C, the angle C. If you notice, if you take this away, right? If you take this away, look what you get. You get the Pythagorean theorem. So C squared equals A squared plus B squared. The law of cosines, in a way, you can call it the generalized Pythagorean theorem. The Pythagorean theorem only works if you have a 90-degree angle. But this works if you don't have a 90-degree angle. And if you notice, if this is 90 degrees, right? If angle C was 90 degrees, cosine of 90 is 0. So when C is 90 degrees, this expression here goes to 0, and you get the Pythagorean theorem. So this is another way you can get the Pythagorean theorem using the law of cosines. Now, if you notice, this is just one formulation of it, which means it's just one version that you can apply to this triangle. So this is if you're using C as the opposite side of this angle C, and then everything else, right? A squared plus B squared minus 2ab cosine C. This is one formulation. The other formulation is if I use, for example, A. What if I use little a? Well, I can write it as this. A squared equals, and I know this has to be cosine of A. This angle has to coincide with the side that's in front of the equal sign. So if this is a squared, then I can write this as cosine a, and then I'm going to fill in everything in. And remember, these sides here are the sides that are not, in this formulation, a and b are not opposite angle C. So what are the sides that are not opposite angle A? Well, the sides that are not opposite angle A and the ones that are next to it are C and B. So I'm going to write this now as this. B squared plus C squared minus 2BC cosine A. So all I'm showing you guys is really the law of cosines has not changed. It just looks different based upon this triangle that I have. It just looks different based upon how I set up my side and my angle here. Once I set this up, then I have this new formulation or version of law of cosines. And then finally, what if I want to use this side here and this angle here and pair these up? So this becomes now what? B squared. This becomes what? Cosine of big B. And then everything else, right? Look at cosine B. Look at the angle B. And what's not opposite? The sides that are not opposite to this vertex B are A and C. So they're going to be left over in this expression, a squared plus c squared minus 2ac. Okay? Law of cosines. That's all it is. This is the law of cosines. Okay, so I'm gonna give you some examples to see this in action. Now let's look at this triangle here. Yeah. So look at this triangle. I got A, I got B, and I got C. Here has my vertices. The opposite side is X. This angle here is 108 degrees. This is 15 and this is 18. So do you see it? Look at the setup. Look at the setup. Eventually, guys, you're not going to be so concerned that what is A, what is B, what is C. You're not going to be so concerned with it as long as you know the relationship between the three sides and the angle. So what do you know? You notice that I have my angle theta is 108 and I have the opposite side is missing, but I know these are paired up. You see that? And then I have the sides that are not opposite 188 degrees, the ones that are next to it or that make up the 108 degrees, 15 and 18. So if you want to be more, if formal, then it looks like, look at angle A. This is the angle that I want. So this is the formula version that I want. What's the side opposite 108 degrees? The side opposite is X. So this is the law of cosines. I want to find X using law of cosines. So what is that going to look like? It's going to look like this. X squared equals, and then I have to add up the squares of the other sides that are not opposite 108 degrees, which is what? 15 squared plus 18 squared minus 2 times 15 times 18 times cosine of 108 degrees. And I want to find X squared. So then this is really just a calculator question at this point. This is 225 plus 324 minus 2 times 15 times 18, which is 540 cosine of 108 degrees. And make sure when you plug in the degrees, you're in degree mode in your calculator. And then you get 225 plus 324 is 549. So I just want to also be mindful, okay? A lot of people make this mistake. You know what mistake they make? They do this. So after they get this, they do 549 minus 540. Don't do that. This is a common mistake. A common mistake is to do this. The common mistake is to say, oh, X squared is equal to 549 minus 540 cosine of 108 degrees. And then they say, oh, this is 9 cosine 108 degrees. This is wrong. You can't subtract. Why not? Because 540 is multiplied first to cosine, then you subtract. PEMDAS. PEMDAS. So at this point, what I would do at this point is I would plug it in my calculator, because you have to have a calculator for this. 108 degrees. It's not a nice reference angle, right? It's not one of those nice ones, 30, 60, 90, 45. It's not. So you get to plug it in your calculator and you get X squared is equal to, what do you guys get? Let me share my screen with my calculator. So I put 549 minus 540. And then I just want to make sure I'm in degree. I am in degree mode. So 549 minus 540 cosine of 108 degrees. And then when I press enter, I get 715. So X squared equals 715.869177. And of course, I want to find what x equals, not just x squared. So then I do second answer. So the answer that I get here is now plugged in there underneath the radical, and then I press enter, and I get that x is equal to 26.7557 dot 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 dot. Okay. So that's how I find the x missing side. I find the side opposite, right? The angle that I'm given. So I'm using law of cosines for this. Once I set up the law of cosines correctly, then it's really just calculator work from here on out. Any questions about law of cosines? So this is the case. This is a scenario where one side is missing. One missing side. So that's when you have one missing side. How do you decide which equation to use? So that's what I was saying, Chen. Eventually these three, you don't even have to worry about which one to choose, because if you start to notice, they're all the same. It's just that the variables are written differently. What I mean by the same is the structure of the equation doesn't change. It doesn't matter if I'm here, here, or here. Do you see the structure behind it? I have one side squared, then I have the other side squared. I'm adding them. For all of them, there's the same idea. Then I'm subtracting what? I'm subtracting double the products of those sides, and then I'm multiplying that with cosine of the angle that's opposite this side. C is opposite big C. A is opposite big A. B is opposite big B. The whole idea is that once you have one side and you have the other angle, that's the pair. That's the pair that's going to, so this side here is going to be x squared like we did here. And then cosine is going to be of 108 degrees. And then you're just going to fill in the other sides, right? 15 and 18. You're going to fill in the rest of the law of cosines. You just fill in the missing sides here. So I'll give you another example, and then you hopefully start to see that it doesn't really matter. The whole A, B, C stuff, it doesn't matter. So let's do another one really quick. So let's say I have a let's say I have a triangle like this. This is 140 degrees. This is 25. Okay, let me just make this. Yeah, this is 25. And this is X. I want to find X, right? I'm just going to set it up. What's the setup? That's the hardest part. Once you get the setup, then everything works out. I'm not even going to use the, I'm not even going to put the names. I'm not going to put the names for the vertices. Just look at this triangle. And then you start to notice, wait a minute. I have an angle 140 and I have the opposite side X. This is the missing side. So I know in the law of cosines, using law of cosines, what does law of cosines tell me? It tells me that the opposite side, x squared, of cosine of 140 degrees, right? This is the setup. And then I have everything else in between. What's everything else in between? I got the 25 squared plus the 25 squared. Then I'm subtract that from double multiplying 25 with 25. So I get 625 plus 625 minus 2 times 625 is 1250, right? So this is minus 1250 cosine of 140 degrees. And then I get this. I get 1250 minus 1250 cosine of 140 degrees. That's x squared. Again, I cannot subtract 125, 1250 with 1250. I can't do that because 1250 here is attached to the cosine. So I have to use my calculator for this. So what's my calculator say? What does my calculator say here? Whoops. So then I get 1250 minus 1250 cosine of 140. And then I press enter and I get 22,000.55 dot 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 dot. And then I want to get just x by itself. So I do the second square root, second this bottom this negative symbol here, and now I got the answer. And so square root of the answer is 46.9. So the answer is going to be 46.9846 dot dot dot. And so that's the missing side. You see here, I did not use A, B, C version. I just recognize what are the angle and what's the opposite side to that angle. Once I recognize that, then I plug in those sides and angle in the respective places of the law of cosines, and then I fill in everything else with the sides that are known. And that's how you set up the law of cosines. Okay, so again, the hardest part of law of cosines is setting up law of cosines. But this is only the scenario where you have one missing side, and we have another scenario when we have the missing angle. And that's the harder version of this, okay? So this is scenario number 2. Scenario number 2 is when you have a missing angle. So when you have a missing side, that's the easier version. When you have a missing angle, that's when you do a bit more. And you have a problem like this. When you have like a triangle, and the angle is theta. I don't know it. The opposite side is 20. The other sides are 12 and 10. So look at this. I have 3 sides, 12, 10, and 20. I have one missing angle. So the first thing I want to highlight to you is theta and 20. These are the pairs, right? This is the side with the opposite angle pair. So because that's the case, then when I use find theta, when I want to find theta, I'm going to use law of cosines. And again, it's all about setting it up correctly. So how do I set this up? Well, the opposite side is 20 squared in this case. And then what's the opposite angle? It's cosine of theta. Theta is now missing. And then I use everything else. I use 10 and I use 12 as the other as A and B in our law of cosines formula. So this will be 10 squared plus 12 squared minus 2 times 10 times 12. So I fill in those missing place values, right, for 10 and 12, because 10 and 12 are the other sides that are not opposite angle. And now I do this carefully. This is 400 on the left side. This is 100. This is 144. This is 240 cosine of the angle. So be careful with the arithmetic here. This is 244. This is 400. This is 240 cosine of the angle. At the end of the day, what do I want? I want theta. That's what I want. And you see how this is a bit different now? Another thing, please do not subtract these two numbers. You can't subtract them. 240 is attached to cosine, so you have to multiply first, then subtract, but we're not going to subtract. We can't subtract like this. And I'm pretty sure some of you might still make that mistake. Don't make that mistake though. Again, I want to find theta. So I want to get theta by itself. So that must mean that I must get 240 out of here first. So yes, you have to subtract 240 first. So subtract 244, subtract 244. And once I subtract this, what do I get? 400 minus 244 is 156, right? So this is 156 equals negative 240 cosine of the angle. Do you guys see that? I'm getting closer to theta. I got to get theta by itself, so I must subtract 240 on both sides. Subtract not subtract, divide 240 on both sides. So the 240s here cancel, and look what I get. On the right side, I get cosine of theta, and this equals 156 over negative 240. Now, how do I get theta? Does anybody know how we can get theta? Of course not. You can't divide. Remember? Cosine theta equals a number. I want to get angle. Yes. Thank you, Tanzila Miranda. Yes, we take the inverse, right? This is you can't divide cosine. You can't do this. That's not how it works because cosine is a function. So what you have to do is do cosine inverse or arc sine of what? Negative 156 over 240. That's what you're supposed to do. So then calculator time. See, another calculator question. It's all about calculator here. You need a good calculator for this. So now you have to take cosine inverse. So you do second cosine, which is cosine inverse. And then you put your, you put your fraction. That's not what I want. Sorry, guys. So this is second cosine, right? And then you do, nope, that's not what I want. You put the fraction in cosine, and then you get, I put negative 156 over 240. And then press enter, and then you get an angle. And the angle here is 130.54 ... degrees. Rounded to the nearest 10, to the nearest 100, to the nearest 1,000. You guys know how to do that. But the idea is knowing how to get to that last step. That's the idea. If you're able to do that, then you're in good shape. Okay? So again, this is the scenario when you have a missing angle instead of a missing side. You set up the law of cosines equation, and then you solve for theta. Make sure you do the arithmetic correct. PEMDAS is crucial here. You have to apply the inverse function for cosine to figure out the angle. And you get that the angle is an obtuse angle, 130.54 degrees. So again, the law of cosines is utilized for any triangle, not just for right triangles. Normally, that's what we're used to, right? We were introduced to trigonometry using right triangles exclusively. However, trigonometry is not just applicable to right triangles, it's applicable to any triangle. And that's why it's very powerful. Law of cosine is very powerful. Okay. Let's do one more of these and then we can move on from here. So this is law of sines. We did that last time. Law of cosines, we're doing it today. All right. So what if I have a triangle like this? And this is 12, 40, and 44. And hopefully you can realize something. Angle theta, I can figure out any of these angles with law of cosines. I can figure out all of them. I just have to set it up correctly. So for example, if I want to find this angle here, call this theta, I'm gonna call this alpha, I'm gonna call this beta, okay? So how do I find theta? Law of cosine. So find theta. How do you find theta? Use the law of cosines. Well, what's opposite theta? 12. So what do you write? You write 12 squared equals, and then the other sides, right? The other sides are 40 and 44. You know where to place them now. 40 squared plus 44 squared minus 2 times 40 times 44 times cosine of theta. And then let's write this out a little bit. 144, this is what, 1600 plus 44 squared is, what is 44 squared? 44 squared is 1936. So 1936 minus, and then you do 2 times 40 times 44. Then you get 3,520 cosine of the angle. Then you add these here. So 1600 plus 1936 is 3536. This is 3536 minus 3520. Cosine of the angle is 144. You don't subtract those two, that 3,000 numbers. You have to subtract 3536 and subtract it on the other side of the equation, so you can get closer to theta. And so this will equal negative 3520 cosine of the angle, and you do 144 minus 3536, and you get 33, negative 33 92. And then from here, I want to find cosine. So divide both sides by negative 3520, negative 3520. You cancel those out. And I get that cosine of the angle is equal to negative 33. A negative divided by negative is a positive. So it's really 3392 over 3520. But of course, I want to figure out theta. So what is theta? Theta is cosine inverse of 3392 divided by 3520. And when you put that in your calculator, I'll put that in my calculator. Second cosine of the fraction 3392 divided by 3520. When you press enter, I get 15 degrees. So 15.4987 ... degrees. That's the angle of theta. Again, I used law of cosines. I set it up correctly. Once I have the setup, then I'm able to slowly but surely with my calculator calculate the different numbers that I have to find. And then I solve for theta using algebra. And of course, I need to apply the inverse trig in this case to find theta. But again, it's the setup that really counts. If you have the right setup, then you got most of it. Okay, I still have a question from one of the homework problems, whatever. Yeah, we can, if we have more time at the end, I'll try to answer your question, Daniel. We still have a few more things to go over. Okay, what I want to say after this is that theta, right? Theta is what we found, but I told you we can find all the other angles. And the other angles, I just have to set it up correctly. So I'm not going to find all the angles. You can do that on your own time. But I just want to show you guys the setup. So to find alpha, how do you find alpha? Alpha, opposite side, 40. What is that? 40 squared equals cosine of alpha. Do you guys see that? And then everything else has to fall into place. 12, you add that with 44 squared, minus 2 times 12 times 44. And that's going to be your, that's going to be the setup. 12 times 44 times cosine of alpha. And then you can find alpha the same exact way we found theta here. And then we do our thing here, and then we find alpha at the end. Or if I want to find beta, then I do what? What's opposite beta? Opposite beta is 44. So 44 squared equals 12 squared plus 40 squared minus 2 times 12 times 40 times cosine of beta. And the same thing is applied, right? Same exact thing. Same exact idea. And like I said, these are all formulations of law of cosines. It's the same version. It's just that I'm applying it. It's the same thing, just different versions. I'm applying it to different angles. So based upon what angle I'm applying it to and what's the opposite side, I'm going to have a different version of the same law of cosines. So you can do that on your own time. Figure out what alpha and beta are using this format. Okay. All right, Daniel, quickly ask me what your question is for the homework before we continue. For question 25, yeah, we did 25. What happened with 25? We did 25. The missing side, Daniel, you have to use the Pythagorean theorem. So I used the Pythagorean theorem. You have to use the information that they give you, set up the right triangle, right? Because I know this is the adjacent, right? This is adjacent over hypotenuse. Because I know that, because this is cosine, then I can create a right triangle opposite adjacent over hypotenuse. And then the missing side, I use my Pythagorean theorem. Well, if it came out wrong, you have to also consider the fact that your sign, you have to know what the sign is. So you can have the right numbers, but maybe the sign is incorrect. So that's something you have to try to see if you're getting it correct. And how do you know what sign it is? It depends upon what angle, where are you in, where is your theta in what quadrant is it in? And you have to figure that out based upon this information here. So if you figure out what quadrant you're in, then you're able to figure out what trig functions are negative. Once you figure out which ones are negative, which ones are positive, then you can find the Pythagorean theorem, using the Pythagorean theorem to find the missing side. And once you have the missing side, then setting up the ratios should be just by looking at the triangle. So try it again, Daniel. I'm sure you'll figure out what the answer is. All right, guys. So this is law of cosines. So we've done law of sines, law of cosines. All right. Now, what we're going to be concerned with is something called simplifying. Simplify. Trigonometric identities. So we're gonna be headed towards more of an algebraic approach for trig. So a lot of the trig we've been doing so far is very geometric, right? You have geometric shapes, you have triangles for the most part, and we're able to figure out what we're doing, or we're making sense of certain trigonometric concepts based upon visualizations of them. For example, the graphs of sine and cosine, we were able to visualize it. The unit circle, we visualize the triangles, law of cosines, law of sines, find the missing side of a triangle. It's all visual, geometric up till this point. From now, though, it's going to be more algebraic. We're going to have almost no visualization of anything. It's going to be purely algebraic. So what are we speaking of? So the identities we've discussed before, right? So recall the Pythagorean identities. So recall, for example, sine squared theta plus cosine squared theta equals 1. This is called the Pythagorean identity. We've talked about this. So what is an identity? An identity is just something that is holds to be true. It's just a true statement. It's a true equation. We're not dealing with variables here. We're not solving for anything. What we're going to be doing is we're going to be showing that an equation is true. That's what we're going to be interested in. But before we do that, we have to learn how to simplify, okay? And I'll give you an example. Very, very basic. So an example of this would be if I have cosine of theta times tangent of theta. Let me put this in front. So I want to simplify this. Simplify. What that means is can I write this expression as something that's simpler than cosine theta tangent theta? Well, the only thing you can try to think about right now is that tangent of theta is also written as sine theta over cosine theta. And what do you notice? Cosine theta cancels, and I'm left with sine theta. So I simplified my original expression. Cosine theta tangent theta simplifies to just sine theta, and I'm done. So that's what we're going to be interested in now. You see how there is no visualization of this? There's no geometric shapes. There's nothing. It's just purely algebraic. Simplify the following. What does tangent of theta times cosecant of theta, what does this simplify to, if anything? Well, what is tangent theta? Tangent theta is sine theta over cosine theta. What's cosecant? Cosecant is 1 over sine theta. Look what happens. Sine cancels. I'm left with 1 over cosine theta. But what is 1 over cosine theta? Also represented as secant theta. So secant theta is the expression which tangent theta cosecant theta simplifies to. Are you guys understanding what's happening here? That's all I'm doing right now for now. I'm simplifying algebraically a trigonometric expression. Let's simplify something a bit more. What if I get this? Cosine squared theta times 1 plus tangent squared theta. What does this simplify to? Now, we have to recall other identities. So this identity here is crucial to know, right? This is like essential. But then we talked about this a while ago. So it's good to recall. From here, remember from here, we can figure out a few other things. So let me move this down. From here, we can figure out a few other things. We can figure out that sine squared theta is equal to 1 minus cosine squared theta. We also know that cosine squared theta is equal to 1 minus sine squared theta. We also know if we divide, remember this, if we divide everything by cosine, for example, you get 1 plus tangent squared theta is equal to secant squared theta. And if you divide everything by sine, you get 1 plus cotangent squared theta equals cosecant squared theta. So these are all the identities that stem from the main Pythagorean identity. Now you have to have this in your head because now look what we have. 1 plus tangent squared theta, I can use the fact that 1 plus tangent squared theta is equal to secant squared theta. So this will now equal cosine squared theta times secant squared theta. But what is secant squared theta? It's cosine squared theta times 1 over cosine squared theta. And then what's cosine squared theta times 1 over cosine squared theta? It's cosine squared theta over cosine squared theta, which equals 1. So what did I just show? I showed that cosine squared theta times 1 plus tangent squared theta really reduces to 1. So let me just show you that I could have done this way. So this is solution 1, right? This is one way. Now let's say you're like, you know what? I have no idea what 1 plus tangent squared theta. I have no idea. I can still have done the same thing. I would have still gotten the same answer. Now let's say I don't remember this, right? I don't remember 1 plus tangent squared theta, but what do I remember to do? Hey, let's distribute. If I distribute, what do I get? I get cosine squared theta plus cosine squared theta times tangent squared theta. But wait a minute, what is tangent squared theta? Isn't cosine squared theta plus cosine squared theta? Isn't this sine squared theta over cosine squared theta? Isn't that what tangent squared is? It's sine over cosine squared. But then, hey, cosine and cosine cancels out. Look what I get. I'm left with cosine squared theta plus sine squared theta. But wait a minute, this one you must know. You must know that this is equal to 1 because this is a Pythagorean identity. Does this make sense? Do you see how in both scenarios I'm left with the same answer? I reached the same answer. I both get 1. And it's supposed to come out with the same answer. Does that make sense, guys? Is this starting to make sense? This is a different feel, a different style for a different flavor, I should say, of trigonometry. Okay, and now let me give you something else. How about this? What is secant theta minus cosine theta all over sine theta? What does this simplify to? Simplify. Like I said, it's a lot of algebra now. So some guidelines, I would say, some guidelines, or I should say, some advice. Okay, advice on simplifying is to do the best in reducing or rewriting trig expressions in terms of sine and cosine. You're not always able to do this, but if you can, try it. Try to always rewrite expressions that you see in terms of sine and cosine because it just simplifies the expression a bit and it actually shows you what you could or could not do. So for example, in this expression here, right, it looks kind of complicated because you have fraction, then you have cosine and sine, and then you have secant in it. The thing is, secant, I can rewrite it as 1 over cosine. Now, look what kind of expression I get here. You can think of this as as a complex fraction. I have a fraction within a fraction. And now how do we take care of that? How do we take care of complex fractions, right? I want to get rid of the denominator. The only denominator that I have here is cosine theta. So my LCD here, got LCD now. LCD here is cosine theta. So what if I multiply the top by cosine theta and the bottom by cosine theta? What happens? Remember the cosine theta here? I distribute it and look what I get. 1 over cosine theta times cosine theta. So this times this here is equal to 1 because it's just a reciprocal, right? And then minus, what's cosine theta times cosine theta? It's cosine squared theta. And what's the denominator going to be? Sine theta times cosine theta. But what's 1 minus cosine squared theta? Didn't we just write this down? 1 minus cosine squared theta is also written as what? Sine squared theta. Do you see that? So I can write this as sine squared theta now. And why did I do that? Because I saw that there's a sine theta in the denominator. And then what do I know? I can cancel out sine theta, one of them in the numerator and one of them in the denominator. And look what I get at the end. I get sine of theta over cosine theta. But what's sine of theta over cosine of theta? Tangent theta. This one took a little bit more effort because it's a little bit more difficult, complex expression in the beginning. But look what I was able to do. I was able to go from a seemingly complex fractional trigonometric expression, and I did a bit of algebra, just a bit, using complex fractions, and I was able to get tangent theta at the end. So this is what we're going to be doing now. Simplifying trigonometric expressions. So the algebra that you learned in the beginning of the semester, or the algebra that we reviewed in the beginning of the semester, now it's definitely going to come back full force. Do you see that? I hope you see that. And now the only difference is now we're dealing with trig. That's it. Now trig is just embedded in it. Any questions, guys? Any questions? I know this is a little bit different than what you're used to. We can go so many different ways with this. Okay, how about this? Cosine theta times secant theta over cotangent theta. What does this simplify into? So what do we have? We have cosine, which is okay, but then we have secant, then we have cotangent. So remember, a tip and advice is try to write the best you can, try to write everything in terms of sine and cosine, and things work out. Let's see if it works out here. So cosine theta, right? I can multiply that by what? 1 over cosine theta, because that's what secant theta is. And then what's cotangent? Cotangent is what? Cosine theta over sine theta. But what's cosine times cosine? Oh, 1 over cosine. The cosine over cosine cancels, and I'm left with 1 over cosine theta sine theta. But what's 1 divided by a fraction? You multiply by the reciprocal. So this is really sine theta over cosine theta. Hey, we just got that last time. Tangent theta. Okay, guys, we have to get very used to this, very much used to this kind of mathematical endeavor here. What if I get this? Cosine cubed theta plus sine squared theta times cosine theta. What do we do here? Well, what you notice, or what you should notice, is that there's a cosine theta, and there's also a cosine theta here, although there's three of them, right? Cubed. I can factor cosine theta. Now, why do I want to factor cosine theta? Because when I factor out the cosine theta, the first term, what happens when I factor out a cosine theta from cosine cubed theta? I'm left with cosine squared theta. And if I factor out the cosine theta from here, I'm left with a sine squared theta. Why is this nice? What's cosine squared theta plus sine squared theta? What does that equal? 1. Beautiful. So this whole thing here that looked complicated, cosine cubed theta plus sine squared theta plus cosine theta, is really just cosine theta. Simplified it. So you also have to be perceptive as to what's possible, what's a correct algebraic step. So factoring can also help. And you should also try to anticipate what may happen. If I do factor cosine theta, what do I have here that's, that I know an expression to? So cosine squared theta, sine squared theta, guys, this is going to be something essential that you have to have now in your back pocket. You have to use it. You have to be able to notice it. You have to be able to recognize it, identify it, because it always equals 1. And if it equals 1, that just goes away. It just becomes 1. Okay, good. So far, so good, hopefully. Let's see what else. There's so many here. It's crazy. How about like something like, yeah, let's start getting there now. So 1 plus sine of theta cosine theta plus cosine theta over 1 plus sine theta. Okay, so this is probably like the harder one now. This is a harder one of these that we've done. So I want to simplify. Now, how do I simplify this? Well, again, this is a algebraic goal that I want. I want to simplify. So what do you notice? I have two different fractions with different denominators. The only way I can add or subtract two fractions is if the denominators are the same. The denominators here are not the same. So what's the least common denominator? What's the LCD among cosine theta and 1 plus sine theta? The common denominator is, what is it? Those different ones, right? Well, the easiest one I think you can think of is just cosine theta times 1 plus sine theta. You just combine the two fractions together. So that's my LCD. The problem is neither denominator is an LCD. So what's missing? What's missing from this fraction here? 1 plus sine theta. Well, what's missing is cosine theta, cosine theta. So I multiply top and bottom by cosine theta. What's missing on the other fraction? Well, cosine theta is in the denominator, and what's missing? I'm missing a 1 plus sine theta over 1 plus sine theta. So now I have 1 plus sine theta times 1 plus sine theta. And this is all over 1 plus sine theta cosine theta plus cosine squared theta over 1 plus sine theta times cosine theta. Do you guys see what I just did there? I made the two fractions the same denominator. Now, because they're the same denominator, what can I do? I can unify the numerators. So 1 plus sine theta, 1 plus sine theta plus cosine squared theta all over 1 plus sine theta times cosine theta. Now what I have to do now is expand 1 plus sine theta times 1 plus sine theta. If I expand it, 1 times 1 is 1 plus sine theta plus sine theta. So I'm foiling, right? Plus sine squared theta plus cosine squared theta. And all of this is being divided by 1 plus sine theta times cosine theta. Does anybody notice anything in the numerator that you already know what that expression is? Does anybody see an identity in the numerator that we can replace it with something? Sine squared and cosine squared. That's right, Chen. So here we have, look what we got. This guy here equals 1. It pops up again. It just pops up sometimes. It just pops up. Boop. So I can replace this now. 1 plus, and then what do I notice about sine theta? Sine theta, it's what? 2 sine theta plus 1 all over 1 plus sine theta times cosine theta. And then what do I get? I got 1 plus 1 is 2. I got 2 plus 2 sine theta over 1 plus sine theta times cosine theta. And then I'm like, okay, I can't do anything else. But wait a minute. I can factor out the 2 in the numerator, and I'm left with 1 plus sine theta over 1 plus sine theta cosine theta. And what do I notice about the 1 plus sine theta? 1 plus sine theta. That becomes 2 over cosine theta, which really can be written as 2 secant theta. So this one took a little bit longer, guys. This one took a little bit longer. But this is the idea. The idea is to apply all the algebraic techniques you have, factoring, LCD, and then along with that is you have to know secant squared theta plus cosine squared theta is equal to 1. You have to be able to recognize that. You have to be able to recognize the other identities. 1 plus tangent squared equals secant squared. You have to identify that cosecant squared is 1 minus sine squared, and that sine squared is 1 minus cosine squared. So there's a lot of thetas and squares and sines and cosines that you hear from my mouth the past 10, 15 minutes. Yeah. So any questions about this, guys? I know this is something that might be a little bit different from what we've been doing so far. You guys have been used to getting answers, getting numbers, and just getting the answer and then moving on. But now this is more of an algebraic action that we're dealing with sine and cosine as if it were just an expression, sine and cosine. We're not looking for theta at this moment. Okay. So once we start getting used to this, right, the next step is what are called proving identities. So proving trig identities. So at first we were simplifying, right? We were just simplifying. We were taking an expression like so, and then we want to figure out what is this equal to. Now we're going to be given something equal. So for example, I'm going to be given cosine theta over secant theta plus sine theta over cosecant theta. I want to show, now this is different, right? I want to show that this is true. I want to show this is an identity that's true. So This is a left-hand side, right? And this is the right-hand side. What I want to show is that the left-hand side eventually becomes the right-hand side, or that the right-hand side eventually becomes the left-hand side. That's what I want to show. So that's why we use simplifying the technique first. So in another sense, does this simplify to 1? Does it? I have to show it. So this is what we do. Left-hand side. This equals cosine theta over secant theta plus sine theta over cosecant theta. That's the left-hand side. And I want to show if I get to the right-hand side somehow. But what is secant theta? And what is cosecant theta? I can rewrite this as 1 over cosine theta plus sine theta over 1 over sine theta. Remember, it's good to always try your best to rewrite secant, cosecant, cotangent in terms of sine and cosine. Now, why does this help? Well, what's cosine theta divided by 1 over cosine theta? Remember, when you divide by a fraction, you multiply by the reciprocal. So it's cosine theta multiplied by the reciprocal of 1 over cosine theta, which is cosine theta. And what's cosine theta times cosine theta? It's cosine squared theta. That's what it becomes when you multiply by the reciprocal. And the same token goes for the next one. Sine theta over 1 over sine theta becomes sine squared theta. But wait a minute, this appears again. What's cosine squared theta plus sine squared theta? What is that? 1. And what is 1? It's the right-hand side of the equation. So I just showed that the left-hand side of the equation, which we started with, equals the right-hand side. So then we say we're done. This little box means like end, like the end of proof. So we just show that the left-hand side equals right-hand side. This is the next step after simplifying trig expressions. So we're going to be continuing this next time.